In this lecture I am going to talk about LL1 parsing, and before we go about describing the LL1 parsing algorithm, we will fix some conventions that we will continue to use for the rest of the lecture. So some basic conventions. So we will say fix a grammar G. Okay, for the name of the grammar would be G. Okay, the terminals of this grammar are sigma equal to A, B, C, etc. And the non-terminals are gamma equal to A, B, C, etc. Okay. Convention here is that the convention that we follow is lower case letters are terminals and upper letters are non-terminals. The grammar can be considered as a string production system. How is that? So consider a string in that is a string of symbols or terminals and non-terminals. Okay. So it's a string which contains terminals or non-terminals. So example is sigma might look like A, capital A, B, C, D, E. Remember that our convention is that small letters are terminals and capital letters are non-terminals, right? So it might look like this. Now let us say A is a rule in the grammar. Okay, so let's say this is the case. Okay, so then we can replace this using this rule AA. Now the capital A can be replaced by alpha, B, C, D, E. Okay, something like this. Okay, so this is one-step derivation. Okay, this is called one-step derivation. Or more formally, we say that suppose sigma is like sigma 1 A sigma 2, then sigma 1 alpha sigma 2 is derivable from sigma in one step. Okay, so this is one step derivation using the rule A of the grammar. Okay, so we might just suppress all these things. We might say that from sigma you go to this new rule. Okay. So if and you can do it in multiple steps. So extend the derive relation to multi derivation. Okay. So we'll use this this picture. So say sigma in multiple steps derives. So this right arrow in multiple steps derives tau if the is a series of derivations, one step. Sigma equal to sigma 0, which is sigma 1, etc. Sigma n is tau. Okay. So what we mean by that is you reach tau by continuously replacing a non-terminal with its right hand side. One can reach tau from sigma by continuously replacing a symbol, a non-terminal with its RHS in the okay, that's the idea. Lemma: the string X is in the language L of G if S derives X in multiple steps. So S is the start. We talk about a more general parsing algorithm. This algorithm input is sigma a string sigma of terminals and non-terminals, and a string X in sigma star. So this is so let me explain this. Sigma is a string of terminals and non-terminals, and X is a string of terminals. Okay. And you have to decide if from sigma can you go in multiple can you derive X in multiple steps. Okay. Decide whether X can be derived from sigma in multiple steps. Okay. Clearly you can see that if you can solve this problem, you can check membership. How? So to check of X in LG, give the input sigma equal to S the start symbol. So your the input sigma is just the start symbol S. It's a string with one letter S. Okay. So if that is true, then you know that by definition string X is in the language. Okay. So the LL1 parsing algorithm or any recursive descent parsing algorithm can be seen as solving this. A recursive parsing algorithm solves the above problem. Okay. So what is the main idea here? The first idea that we want to talk about is, suppose sigma looks like A times some alpha, okay, where A is, by convention, A is a terminal. Okay. So any string that you can derive from sigma should look like, so any string one can derive from sigma will look like a y. for some y in, right? Because the first character is fixed here, yeah. So you can't do much. Okay. So suppose, okay. So this is an observation. So then the point is sigma in multiple steps derive x if x looks like a times y and alpha in some multiple steps derive and only if. Yeah, so this one. Second idea is that if sigma looks like, so if sigma starts with a non-terminal, so okay, then sigma derives x if and only if there is some production gamma such that gamma alpha derives x. Okay. So what we are doing is we are doing the leftmost production here. So we try to expand the leftmost symbol at each step. Okay. And when we hit a terminal, we just eat it up. Okay. So the recursive descent parsing algorithm just recurses over here, just tries over all the productions of A. Okay, that's what it does. Okay. And backtracks and finds. Okay. So this is what the algorithm does. So from the first point, you can also see that if x looks like b times y for some b not equal to a, then sigma cannot is not possible. So those cases it can backtrack. Okay. But this is a hopelessly it's not even clear whether it will terminate. Okay. So LL1 is a slightly cleverer way of doing it. Yeah, is more version of this algorithm, but it need not work for all grammars, but it need not work for all grammars.